Helium atom. Consider a simple model of the helium atom in which two electrons, each with mass m, move around the nucleus charge plus 2e in the same circular orbit. Each electron has orbital angular momentum h bar, that is, the orbit is the smallest radius Bohr orbit, and the two electrons are always on opposite sides of the nucleus. Ignore the effects of spin. Part A, determine the radius of the orbit and the orbital speed of each electron. Hint, each electron experiences an attractive force from the nucleus and a repulsive force from the other electron. So if you look at the situation, nucleus has charge plus 2e, two electrons on two opposite sides of the nucleus. They are traveling in the same direction in the same orbit. So each electron feels a centripetal force due to its interaction with the nuclear charge and also a repulsive force due to the other electron on the other side of the orbit. And we are given that the angular momentum L is equal to h bar for these electrons. That is to say, we're talking about n equals 1, a Bohr orbit, and we want to know the radius r, determine the radius of the orbit and orbital speed v. And we know that according to Bohr model, the angular momentum mvr is quantized, so it is n is equal to 1 here, corresponds to h bar. The centripetal force, F centripetal, is ke square, k2e square over r square, and then we have also the repulsive force between the two electrons. So the total force an electron feels is the centripetal force, which is k2e square divided by r square. And then we have the repulsive force ke square divided by the distance between them here, because they're on both opposite sides of the nucleus, is 2r. So 2r parenthesis square, that's 4r squared. And this must be equal to the net centripetal force is equal to mass times the net centripetal acceleration, mv squared over r. And you can see that one of the r's disappear. And I can take this equation and multiply it by mr squared. So if I do that, I will get mke squared, and here is the first term, 2 over r squared will get rid of this r squared, so I will have well, it's 2r squared divided by r, so that's 2r. And then for the next term, I have minus r over 4. So you can see 2ke squared over r multiplied by mr squared gives me 2ke squared mr. Ke squared over minus 4r multiplied by mr squared gives me mke squared r over 4. This is equal to the right hand side mvr parentheses squared. That means it is h bar squared, because mvr is h bar in this problem, and Coulomb's constant k is 1 over 4 pi epsilon 0 permittivity of free space. Okay, now we have 2r minus r over 4, that's 7r over 4. mke squared, 7r over 4 is equal to h bar squared. That means the radius of the orbit r is 4h bar squared divided by 7 mke squared, or if I substitute for k 1 over 4 pi epsilon 0, r is 16 pi epsilon 0 h bar squared divided by 7 m e squared. So I've substituted for k 1 over 4 pi epsilon 0. This is the radius of the orbit. And since I have the Bohr radius A0 is equal to h bar squared divided by mke squared, known quantity, this is 0.529 angstroms, and r is equal to 4 divided by 7 Bohr radii. Therefore, I can find my r, the radius of this orbit, to be 0.3 angstroms. That was the answer to the first question in part A. Now I'm supposed to find the orbital speed, v, and v is mvr is equal to h bar. That's the angular momentum. So v is equal to h bar divided by mass times the radius. So that is h bar divided by the mass times the radius is 7 me square. So 1 over the radius is 7 me squared divided by 16 pi epsilon 0 h bar squared. So one of these h bars disappear and these m's disappear. And I find that the orbital speed v is equal to 7e squared divided by 16 pi epsilon 0 h bar. Okay, and I can calculate this. V is equal to now you can see that this is h bar over m 1 over r. So h bar is, I'm using this result here, h bar is 6.63 times 10 to minus 34 joule seconds divided by 2 pi. Mass of the electron is 9.11 10 to minus 31 kilograms, and r is 0.3 angstroms, so this is going to be divided by 0.3 times 10 to minus 10 meters. And finally, I get the orbital speed to be 3.86 times 10 to 6 meters per second. So that's the answer to part A of the problem. Part B, what is the total kinetic energy of the electrons? Now, since I know the orbital speed, I have 2 electrons. The total kinetic energy will be twice 1 over 2 mv squared. They each have the same orbital speed. So this will be k is equal to mv squared. So it's 49 m e to the 4th power divided by v squared 256 pi squared epsilon 0 squared h bar squared. That's the total kinetic energy. And I can calculate this kinetic energy mv squared 9.11 times 10 to minus 31. V is 3.86 times 10 to 6 meters per second. So mv squared will be equal to 1.36 times 10 to minus 17 joules. If you divide it by the electron charge, 1.6 10 to minus 19 coulombs, you obtain 84.8 electron volts for the total kinetic energy. Part C, what is the potential energy of the system, the nucleus and the two electrons? The potential energy is minus 2ke squared divided by r, potential energy of one electron times 2 due to the presence of the nucleus, plus ke squared over 2r, the repulsive potential energy between the two electrons. This gives us 1 minus 8 ke squared divided by 2r. So we find that the potential energy is minus 7 over 2 ke squared over r. So if we substitute for k 1 over 4 pi epsilon 0, the total potential energy is minus 7 e squared divided by 8 pi epsilon 0 r. So that's substituting for k 1 over 4 pi epsilon 0. Numerically, we can calculate it. The potential energy is U is equal to minus 7 electron charge, 1.6 10 to minus 19 coulombs squared, divided by twice the radius, 2 times 0.3 10 to minus 10 meters, and multiplied by Coulomb's constant, 9 times 10 to 9. That gives us a potential energy of minus 2.69 times 10 to minus 17 joules. If I divide it by the electron charge, 1.6 10 to minus 19 coulombs, this is minus 168 electron volts. That's the total potential energy of the system. Part D, in this model, how much energy is required to remove both electrons to infinity? How does this compare to the experimental value, 79 electron volts? The total energy of an electron in such an orbit is its kinetic energy plus its potential energy. Kinetic energy we have found to be 84.8 electron volts, potential energy minus 168 electron volts. So we get a total energy of minus 83.2 electron volts. Okay, now this value, this is within what percentage of the experimental value? 83.2 minus 79 is the experimental value, divided by 79 times 100, which is 5.3% of the experimental value. Okay, so we find that the energy required is plus 83.2 electron volts required to remove the electrons and separate them to infinity. That's what we find as our final answer in part D. Okay, so we are talking about a model for the helium atom with two electrons in the same orbit, n equals 1, first Bohr orbit, angular momentum h bar, and the positive charge at the nucleus is plus 2e. In part A, first we looked at the total force acting on a given electron, the attractive force due to the nucleus, and repulsive force due to the other electron, and set it equal to mass times the centripetal acceleration, and multiply the equation by mr squared to get angular momentum squared on the right hand side, so that we can substitute for angular momentum h bar. This allows us to calculate the radius of the orbit in units of the Bohr radius here, h bar square over mke square. This is actually 4 over 7 times the Bohr radius, 0.3 angstroms. And then we calculated the orbital speed by looking at the angular momentum, mvr equals h bar, and substituting for r what we have found. The total kinetic energy is twice the kinetic energy of the two electrons, mv square. We can just substitute what we have found for V here to calculate it. The total potential energy is due to the attraction of the two electrons to the nucleus minus 2ke squared over r for each of them. There's two of them, and plus the repulsive potential between the two. And this allows us to calculate the total potential energy. When we add the potential energy to kinetic energy, we find the negative energy plus this energy, positive value of this energy, must be supplied to remove the electrons to infinity. And the answer is within 5% of the experimental value.